Okay, so just a really quick review on that real fast. The red area, the first two columns, and the slide, type 1, metal name, non-metal, change to IDE. Type 2, which is the D, the F, and the lower P, not including the slide. You name the metal, use a Roman numeral for the charge of the metal. The non-metal still changes IDE. Now, type 1 and type 2 could be with a polyatomic. Don't change the ending of the polyatomic. Just name the polyatomic. Type 3, 2 non-metals, so or a non-metal and a metalloid. That's on the diagonal line or above, and that's when you use a monoditri. Only use mono on the second element. You never say mono for the first element. Then type 4 was just with hydrogen. It's where you have an acid. If you had just hydrogen and one other element, then you have that hydro, whatever, ic and acid. So the hydro is the key word here. If it was a polyatomic, you would just have ic and acid, so you would convert that back to 8, look for the polyatomic, balance it out with the charge of hydrogen. If you had OS, remember OS we're going to get in a fight, so we go back to ite, look for that, and balance it out with a hydrogen. So now we're going to practice some. So, if I can go forward. There we go. All right, so here we go. I'm going to put a few of them up on the board, and I'm going to have you try them and see what you can do with them. Okay, I'll give you a few seconds to try these on your own, and we'll see how you do. Hydro tells you what? Hydrogen and one other element. So hydro tells me hydrogen and only one other element. So I don't look at polyatomics. Yes?
I just have a question on like adenine.
Okay.
So I'm doing chromium nitrate, and so when I get to here, where do I put the parentheses?
So the parentheses goes around the nitrite, and the 3 goes as a subscript.
So up there or
down? Down. Subscript means below. Okay, so if you're having trouble, we're going to go through this slowly. Hydro tells me it's just hydrogen and one other element. So I know it's going to be an H+. The other element is iodine, which is a minus. So then I just put it together, HI. If I were asked to draw what was going on there, I would be saying H had 1 dot, and since this is covalent, I'm going to have to move that around so I can actually have it where it needs to be. H has 1 dot, and we have iodine coming in and sharing that. So that's the covalent bond there. Okay, sulfurous acid. Again, I have my H+, because the acid always tells me I've got H+. Sulfurous came from ite, so I'm looking for sulfite. Sulfite is SO3. I can get that from the back, and it's a 2 minus. So I'm going to need 2 hydrogens to balance that out. H2SO3. Okay, and I could do the Lewis dot for that one too. Chromium. Remember, the Roman numeral tells me the charge on the one before it. So chromium has a 3+ charge. Nitrite, since it's an ite or an 8, I'm going to look on the back of my periodic table, find out what it is. It's NO2 and has a -1 charge. So I need 3 nitrates to go with a chromium. So I have to put those nitrites in parentheses and say I need 3 of them. Okay? All right, disulfur trioxide. The prefixes tell me how much of each one. So S2O3, done. Next one, aluminum sulfate. Aluminum is part of our slide. It has a 3+. Sulfate, again, 8 on the back of my periodic table, is SO4 with a 2- charge. Common factor here is 6, right? So I would write Al2SO4 3. I did that over there, sorry, because I can put it over here. Al2SO4 3, because I want to show what's going on with this. So when I put these together, I would need 2 Al3 pluses to go with 3 SO4 minus. So if I was to draw it as ionic, that's how I would draw it. Okay? If we're just using 2 elements, then I would show the Lewis dots around them too. Okay, phosphoric acid, ick, came from 8. Acid tells me I've got a hydrogen. Phosphate is PO4. It's a 3-. So I need 3 hydrogens to balance out the charge. H3PO4. Yes? I got dishes back in the back if you want to do dishes in the very, very back. Okay? That's about all I've got. So in the very, very back, there's some dishes need washed. On that table in the back lab before you turn the corner, there's some gloves. Okay? All right. So, turn. There we go. All right. Do we want to do more? Do we want to do more of a specific type? You are going to need to draw and show me where the electrons are drawing, like in an ionic bond. You know how we showed this electron's moving here, and then it became a positive and negative. We can do some of those. If it's a covalent bond, you just show it being bonded. Okay, so we'll do an ionic and a covalent. So let's do Mg and Br. Okay, so if I'm going to put those two together, first thing I do is write each Lewis dot. So how many does Mg have around it? 2. Then I write Br's. I'm going to pick a different color. Br has how many around it? 7. So 1, 2, 3, 4, 5, 6, 7. Okay, so Br needs 1, but magnesium has 2. So what does that tell me right away? We need 2 bromines. Good. So we have another bromine. And then I go and I show where these are going to move. I'm going to show it moving here, and I'm going to show one moving here. After I do that, then to write the final for it, I would say magnesium now has a 2+ charge. Whoops, let me get this a little bit fixed. I'm going to move it over a little bit. Magnesium has a charge of 2+ because it's lost 2. And bromine will now have 8 around it, right? And it will be a negative charge. And one will be on that side, and one will be on this side. Why do I put them on different sides? Where they would have attached, where they would have had to get their electron. Okay, so that's an ionic bond. So that's what I would have to do for an ionic bond. Okay, so if we were doing a covalent bond now, and say that I was doing nitrogen with hydrogen, nitrogen has how many around it? 5. So 1, 2, 3, 4, 5. Hydrogen has how many around it? 1. So nitrogen needs 3, hydrogen needs 1. So how many hydrogens am I going to need? Okay, so I'm going to need 3 hydrogens here. Okay, so when I go to put this together, remember covalent bonds aren't strong enough to pull it apart and get the positive and negative. So I'm going to put nitrogen in the center. I'm actually going to draw the molecule together. So here is where the hydrogen's going to go. Here is where another hydrogen go. Here is where another hydrogen's going to go. Okay, what shape? Trigonal pyramidal, because we've got one unshared pair of electrons. Okay, so trigonal pyramidal.
Heather Hansen, please come to the
Okay.
office. Heather Hansen,
Yes.
please come to the office.
When you have 3 elements that you need to do that with,
Uh-huh. You want to do 3 different ones? Okay. Okay, so we're going to do 3 different ones. Let's do HCN. Okay. So hydrogen, again, had 1, right? Whoops, I should probably pick a different color for hydrogen. Let's pick green. Carbon, because carbon's always black, has 4. And nitrogen, which is always blue, has 5. Okay, so how do I decide which one's my middle one? Why did you pick carbon? Carbon usually is in the middle, that's true. Carbon is the one that needs the most right now, right? It needs 4. So it's the most needy, so we're going to put it in the center. So since it's in the center here, I'm looking now at the others before I put any of the dots on. And I say, okay, hydrogen needs 1, nitrogen needs 3, 3 and 1 is 4. That takes care of all carbons, right? So if carbon's going to share 3 with nitrogen, we can set it up like this, and it's going to share 1 with hydrogen on this side. So I can put my hydrogen in. I can put my nitrogen in as sharing 3. That leaves 2 that are not shared, so they're going to go exactly opposite. Now remember, once we do this, we don't want to leave the dots because that's a lot of dots. So we go carbon is attached to hydrogen and triple attached to nitrogen with 2 extra left over.
what kind of bond is that?
Triple bond. 2 hands and a knee. Okay? All right. Do we want to do any others? Look at your review sheet, your review paper. Is there any others that you had problems with that you'd like to go over?
What is happening with electrons in a metallic bond?
Okay, so in a metallic bond, a metallic bond basically has atoms of, say, copper or zinc or tellurium, or they just can be random in here. We'll put a uranium in there. That's not really happy, but that's okay. Another copper. So it can have a lot of different things in here. What happens with the electrons is they are free-flowing. So they are a sea of electrons, and they can move anywhere they want to. They're just sort of moving around in the sea of electrons, where the metal ions or the metal atoms that are in the center there are just like houses on a block. And the electrons can move around that block however they want to. Okay, so they're what we call the valence electrons here are free-flowing. And that allows them to conduct electricity, allows them to conduct heat, allows them to do whatever, shine. That's why metals shine. Okay, that's because their electrons can move wherever they want. They're not stuck in that outer valence shell. Okay, anything else?
Can you do the example of like the Roman numeral ones?
One more time. Example of?
The Roman numeral ones.
Oh, the Roman numeral ones. Okay. So Roman numeral 1. Let's do okay, so tungsten for sulfate. What is the symbol for tungsten? W. Okay. What does the Roman numeral IV mean? 4. What does that tell me? It's a charge on tungsten. Good. And sulfate. What is sulfate? SO4. And what charge does it have? 2 negative. And I got to get that off the back of my periodic table. They were in the very, very back by this still, right across from the still. Uh-huh. The ones that were off to the side of it, too? Okay, awesome. Okay, so what's the common factor here? 4. So tungsten's already at 4, right? So we only need one of them. How many sulfates do we need to make it to -4? 2. So since it's a group, we put it in parentheses, and we put 2 on the outside. Okay, you want to do another one? Okay. How about Yep. So what does the IDE tell me? Just an element with 2 exceptions. What are the 2 exceptions? Do you remember? Hydroxide, which is OH, and cyanide, which is CN. So those 2 are on the back. So if you look for hydroxide, you can't find an element hydroxide, it's on the back. Can't find an element cyanide, it's on the back. Okay. It'll be on the back of the periodic table you get. Okay. All right. So starting again here, copper is what charge? 2 plus. Good. Phosphide, what charge? 21. Okay. Oh, 2 plus. Sorry. It's like 21. No, not quite. All right. It didn't catch the other one. Okay, so phosphide. How do I find the charge on phosphide? It's 3 minus because it's 3 away from being a noble gas, so it's a -3. Okay, common factor, 6. How many coppers do I need to times this by to get to 6? 3. So Cu3. How many phosphoruses do I need to have to make it 6? 2. So P2. Okay. Any others that you'd like to go over? Yes. Okay, so electronegativity determine the type of bond. Okay. So over here, noble gases are 0. Okay, fluorine is high, francium is low. So everything trends between francium to fluorine. Okay, that's with electronegativity. So the farther apart 2 elements are on this chart to go together, you're going to be ionic. The closer you're getting together, polar covalent. If they're right next to each other, covalent. That's the easiest way to do it. Okay, farthest apart, ionic, francium. So farthest apart, ionic, closer together, polar covalent, right next to each other, covalent. Okay, now that changes up when we do atomic ionization energy. Because ionization energy now, this is the highest with helium. So it just sort of extends out and becomes highest at helium. But it's still the same direction. That's the ionization energy. That's the amount of energy it takes to take an electron away.
And what about when it has hydrogen?
So hydrogen's just over here, it does whatever.
So if hydrogen's say like 4 or something.
So you've got to remember the electronegativity of hydrogen is like 2.2 and fluorine's about 4. So you're going to be not, you know, if you're doing it with fluorine, then you probably have more of an ionic bond. But if you're doing it with carbon, it's not.
For the CE, do I have all these electronegativity?
It will give you the ones you need. Yes.
But where are the desired thresholds?
So 0.5 and 1.7. Yeah, 0.5 and 1.7. Yes.
So how do you know, I forgot the term, but how do you know if like one element is stronger than the other? That one.
Okay, so the closer I get to fluorine, the more it wants an electron, so it has a higher electronegativity and a higher ionization. Okay, the farther away, lower. Okay, yes?
So you said P and S have, they break the octet rule, so how many can P and S have?
P is 4, S is 8. Yes,
So then, like, oxygen has a higher ionization than sulfur,
right. So if I go up a row and I'm getting on the row that fluorine's on, I'm going to have higher ionization because it's a shell closer to the nucleus. Do you need me to sign something real fast, real quick? Okay. Uh-huh. All right. Anything else you'd like to go over?
I have a question on the pose though.
Okay. Number one, the solution with some molecular compounds are good connect. That's because they actually connect to each other and they're interconnected. So like graphite will conduct because it's interconnected. Okay, any other questions? Okay, CE, do you have any questions? Yes. Mm-hmm.
So how do you do this one with?
Okay, we got a question with CH3Cl, right? That's what it was?
No, it's CL.
Cl3H. Okay, let's try that. CHCl3. That one? Okay, so carbon has 4. Chlorine's actually in green, so I'm going to do it in green. And we'll let hydrogen be blue this time since I only have 3 colors. Okay, so again, carbon's probably going to be our center because it needs the most, right? So we're going to put it in as our center. We're going to put our 1 hydrogen in. Doesn't really matter where I put it. And we're going to fill the rest with our chlorines, right? Okay, what shape is it going to be? What shape's that going to be? Tetrahedral, because it has 4 things attached. Good. So I'm going to just draw one without the extra dots on our chlorine. So we have a hydrogen, we have a carbon, we have a chlorine going back into the wall, and then we have another chlorine coming out at us. Is it polar? Well, the chlorines are going to be a little bit negative because they're closer to fluorine. So this side is a little bit negative. Hydrogen is going to be a little bit positive. So guess what? It is a polar molecule.
And then how do you tell just individual bond if it's polar or non-polar?
Any bond is polar if they're not the same. So if they're the same, non-polar. If they are not the same, then they're going to be polar. Okay? And I need to be able to write on this where my positive and negative are. So the one that's the closest to fluorine is going to be the negative, the slight negative. The other one's going to be a slight positive.
Slight negative, close to fluorine, right?
Right. Closer to fluorine is you're going to be your negative side. Okay, anything else? Okay. So I'm mixing in here, sorry, some CE and some general. So if you're general and we haven't talked about it, it's okay. Breathe. What? I don't remember if I gave them, did I give you the shapes? I can't remember. I'm getting CE and general mixed up. I know I gave CE the shapes, but I don't know if I gave general shapes. Just band, trigonal pyramidal, tetrahedral, just the basic ones. Trigonal planar, it doesn't have the dots. I don't think we did in general.
Thank you, Miss L.
Yep. Okay, any other questions? Last chance. I'm wishing you luck. I'm wishing you luck. Okay.